morning to one and all. I am bm.manoj Kumar. I am pursuing my mechanical engineering in BATM Ballari College. My USN is 3BR16ME020 and I am here to explain about the topic Design and Development of Spray Automation for Light Structure Alloys under the guidance of Mr. Raghavendra Kodi sir. These are the following contents: Introduction, Principle, Literature Survey, Abstract, Methodology, Rapid Solidification, Process Description, Applications, Advantages and Disadvantages, Objectives, Outcomes, References, Conclusion. Introduction. Spray automation is the transformation of a liquid into a spray of fine particles in a vacuum or a surrounding gas. A spray nozzle is used to generate the atomized spray which passes through an orifice at high pressure and in a controlled manner. The conversion of bulk liquid into a dispersion of small droplets ranging in size from submicron to several hundred microns in diameter is of importance, as in many industrial applications such as spray automation, spray combustion, spray drying, evaporative cooling, spray coating, drop spraying, and as it has many applications in medicine, meteorology, and printing. Numerous spray devices have been developed which are generally designated as atomizers, applicators, sprayer, nozzles, etc. Spray forming also involves sequential gas atomization of melt into a spray of fine droplets deposition on a substrate to build up a high density perform. The rapid solidification inherent in spray deposition generates redefined, equated, and low segregation microstructures. Working principle. The following figure shows the diagram of spray atomization process in rapid solidification. Here, the metals on which we are working is molted into a furnace up to its superheated condition, and then it is poured into a crucible. The crucible is placed on the table having small hole gap at the bottom where a nozzle is fixed for spraying purpose. The stopper rod is used to stop the flow of molten metal. The inert gas pipeline is attached to the nozzle setup for pressuring the spray of molten metal and also a preheated coil is connected to nozzle to maintain the constant temperature of molten metal throughout the process. The elevating table, which is placed at the bottom of nozzle, is used to correct the molten metal, and the table moves up and down according to requirement. Literature survey. Sharma discussed on microstructural. Several attempts have been made to improve the mechanical properties of aluminum, zinc, magnesium, and copper alloys. Much of the progress achieved in the development of aluminum alloys can be attributed to the new production methods such as powder metallurgy and spray deposition. These methods utilize the rapid solidification process, which allows increased compositional latitude while avoiding common problems associated in conventional ignite metallurgy such as alloy segregation and microstructural coarsening. K.V. Oja also studied on microstructural and spray formed aluminum silicon, which are widely used in aerospace, automobiles, and electronic industries due to their high strength to weight ratio, excellent wear and corrosion resistance, good casting ability, and low coefficient of thermal expansion. The silicon phase in aluminum silicon alloy provides all the above mentioned properties. Abstract. The purpose of this technical manuscript is to present an explanation of rapid solidification process in an easily understandable manner so that the technique is widely accepted and put to commercial practice by many working in the industries of material processing and in manufacturing engineering. To better understand rapid solidification in comparison with conventional solidification, the intrinsic accepts and types of nucleation and the kinetics governing nucleation and the subsequent growth of the crystal during rapid solidification are presented and discussed. We highlight the key findings of selected studies in the area of rapid solidification processing of advanced metallic, intermetallics, and composite materials that have developed to advance the processing technique for emerging applications that is synchronous with advancing technology. Rapid solidification. Rapid solidification may be defined as a sign as the rapid extraction of thermal energy to include both superheat as well as latent heat during the transition from liquid state at high temperature to solidify material at room temperature, also known as ambient temperature. Rapid solidification is a metastable process that results in a significant under cooling of the molten metal, leading to a refinement of microstructural features and constitutional effect, such as solubility limits, crystallization phase, high strength, stress corrosion resistance, ductility, fracture toughness, fatigue crack, etc. Methodology. This is a block diagram which contains the steps or methods in which the process occurs. First, design and development. Second, experimental and spray automation. Third, microstructure and characterization. Fourth, mechanical characterization. Spray automation experimental setup for light structure alloys. The following figure. Here, if you watch the following figure, you can see a furnace which is situated at the top, which is like a U-shaped bucket in which the liquid or the molten metal is present and it is heated at superheated condition. So when the liquid turns into molten metal or liquid droplets, a stopper rod is used which is used to maintain the flow and regulate the movement of the hot molten metal. A nozzle is present just below the furnace which passes the hot molten metal and it sprays on the billet or the substrate. Here an inert gas cylinder is placed which is controlled by a control valve, and the working of this inert gas cylinder is that it provides adequate pressure to pass the hot molten metal from the nozzle and to spray it on the billet or the substrate. And on the bottom we are having a table which can be moved vertically up and down so that the following substrate or the workpiece on which the deposition is to take place can be worked properly. Here in this figure, a copper strap plate is placed on which the fine droplets of the hot molten liquid is sprayed and the deposition takes place. So if you watch the figure, here we have a cold water. From the right side a cold water is passed in, and from the left side the cold water goes out. The purpose of the water is that it absorbs the heat and it carries away the heat to outside. Process description. As mentioned earlier, spray automation is the transformation of liquid into spray of fine particles in a vacuum or surrounding gas. A spray nozzle is used to generate the atomized spray which passes through an orifice at high pressure and in a controlled manner. It means the conversion of bulk liquid into a dispersion of small droplets ranging in size from submicron to several hundred microns in diameter is of importance in many other industrial applications such as spray combustion, spray drying, evaporative cooling, etc. If we consider the figure, there the melt is first guided from a tun dish via a ceramic casing nozzle to a concentric atomizing gas nozzle. The melt jet is then dispersed to small droplets by an inert gas according to the figure 1. The average droplet diameter is about 60 micrometer. Compared to the metal powder production, the mass flow rate is significantly higher, namely up to 35 kg per minute with a single atomizer and up to 70 kg per minute with a twin atomizer. The primary gas nozzle runs with a slightly elevated pressure and is used for guiding the melt jet. Figure 2 shows a typical spray forming arrangement. The melt is prepared in a metallic furnace and then transported to the spray forming plant with a holding furnace, and it then flows through an inert gas tube into the tun dish and from there through a casing nozzle to the atomizer. A controlled stopper rod keeps the melt level in the tun dish and therefore the mass flow rate constant. Bottom pouring and storing of the melt surface keep off oxygen coming from the surrounding air. The spray chamber is also flooded with inert gas, and the gas here used is usually nitrogen. The atomization is similar to the production of metal powder, but the distance of the droplets during spray forming is significantly shorter. Just before complete solidification, the droplets hit a suitable substrate which rotates and can be moved in vertical direction by using the shovel and solidify. A metal layer is formed and grows according to the flow rate of the droplets. Proportional to the growing layer, the substrate is withdrawn in order to keep the distance between the atomizer and the tip of the billet constant. The angle between the axis of atomizer and the billet allows the diameter to be controlled merely by adjusting the withdrawal speed. Here, the figure 3 shows the finished billet after the end of spraying process with the open spray chamber, and the figure 4 shows the billet being formed shortly after the beginning of the spraying process. The maximum diameter reached up to now is 500 mm. So, considering the figures, the left figure shows the figure of the atomizer, or the process in which the spray deposition takes place. It consists of the following parts: holding furnace, turn dish, atomizer, billet, withdrawal, exhaust gas, overspray container, spray chamber, and particle injector, which is shown in the left side. And the right side figure shows the billet formed, or a view inside the spray chamber at the beginning of the process. Here, the left figure shows a layer of deposition of fine particles on a substrate or a section of solidified CuSN135 with the phase, which is on the left side, and the right side shows an alternate chamber through which the spray deposition can also be achieved. Now let us consider an example. Let us consider spray forming of aluminum alloy. The following diagram shows that the hot molten metal is passed from a chamber through a ceramic nozzle and it is sprayed on a billet. So when the layer of deposition takes place on the billet, and the deposition is collected and rammed, and through overspray it is sprayed outside. It consists of the following steps: continuous gas atomization of a melt stream to produce spray of 100 to 500 mm diameter alloy droplets cooling at typically 102 to 104 meter per second, and acceleration to 50 to 100 meter per second under the action of atomizing gases. Deposition of gases at the growing spray formed billet surface. Relatively slow cooling at 0.1 to 10 meter per second, and solidification of any residual liquid in the spray formed billet. The left figure shows the figure of microstructural permanent mold cast, which is formed after the spray deposition on the surface, and the right side figure shows a workpiece or a billet which is CuCsZr, which is of dia 500 mm. The typical applications of spray deposition are shell tubes for superconductors on the basis of NB3SN, springs in contacts, connectors for high frequency engineering, sliding elements such as slippers and machine bushings, plastic injection molds or gas injection molds, forming tools for the deep driving of stainless steel. Advantages. Some of the advantages are low processing temperature coupled with high heat extraction reduces segregation and coarsening. Inert atmosphere maintained during process reduces the potential for defect formation in the microstructure. A relatively homogeneous distribution of non-metallic phases such as oxides, nitrates, silicons may result in dispersion strengthened materials. Potential for producing alloys with compositions beyond those that can be produced using conventional processing methods. Low tooling costs coupled with reduced energy requirement and high throughput could make this an attractive rapid prototyping tool. Microstructural homogeneity possible in this process allows it to be used, for example, to make sputtering targets, example aluminum, neodymium alloys, and fine grain sizes, reduced size of secondary phase and metastable phases. Disadvantages: it requires further remedial steps such as rolling, extrusion, or hot isostatic pressing. Metal losses because of overspray, that is, atomized droplets that do not arrive at the platform. Objectives: the objectives are superior protection against metal rust and oxidation, to improve the mechanical properties, to improve microstructure of metal, rapid solidification, to optimize structural parameters. Outcomes: some of the outcomes are grain refinement by increasing cooling rate, increasing the solid solubility of one metal in another metal, uniform distribution in secondary phase can be achieved, improved in mechanical properties to enhance the yield strength and ductility. Conclusion: spray forming is a fairly new process. Introduction into industrial production is still in its beginnings. However, it offers interesting production possibilities on the hand for materials already known which cannot be cast or are difficult to cast, and on the other hand for innovative materials with special properties. So, tin bronze up to 17% SN
can be produced by spraying foaming without additional homogenization, that means with excellent ductility and high mechanical strength. The border between cast and wrought materials is shifted to higher tin contents. Multi-phase structures can be adjusted by heat treatment if necessary. Therefore, it allows a good hot and cold reduction. This is an average for special slide bearing application. References. These are the following references which I have referred and made this seminar. Thank you.